and touch a metal object, you sometimes get a shock. The shock is caused by the sudden flow of electrons between your body and a conductor, in this case, the metal tap. The atoms which make up a conductor are thought to consist of positive ions, with a number of loosely held electrons, which move at random, drifting towards one nucleus and then another. Opposite charges placed at each end of the metal cause these electrons to drift from the negative end to the positive end as they proceed in their random motion. Ions also experience forces of repulsion and attraction, but if the material is a solid, they will not be able to move about freely. Transfer of a charge through a solid can only be accomplished by the motion of electrons. But why does taking off a sweater result in electrostatic charges? Before you get dressed, both the cotton shirt and the wool sweater are electrically neutral. When the wool and the cotton come in close contact, however, things begin to happen. As a group, the atoms making up the cotton fabric have a stronger attraction for electrons than the atoms making up the wool. As a result, some electrons transfer from the wool to the cotton. When the first electron transfers to the cotton, the overall charge of the cotton changes from neutral to -1. But the charge on the wool has changed as well. It has one more positive than negative, resulting in an overall charge of +1. As more and more electrons are transferred from the wool to the cotton becomes more and more negatively charged. And the wool becomes more and more positively charged. There's a limit, however, to the number of electrons which can be transferred before the positive charge on the wool begins to attract some of them back. Both the cotton shirt and the wool sweater consist of billions and billions of atoms. So instead of trying to show all the charges, we'll just show a representative sample on each garment. When the two materials come in close contact, we can show the charge transfer from the wool to the cotton in this way. The cotton, with its excess of electrons, becomes negatively charged. The wool, with its deficiency of electrons, becomes positively charged. Note that during the process, the positive charges never move. Both the cotton and the wool are good insulators, so the charge transfer is limited to where there is contact between the two. If you are wearing a negatively charged shirt, how can you neutralize it? Easy. Simply touch a metal water tap. The excess electrons will transfer from your finger to the tap until the negative charge on your shirt balances the positive charge. The pipe to which the tap is attached runs deep into the ground. This connects to the Earth, which is neutral in charge. Because of its vast size, the addition of small amounts of charge, or its removal, does not significantly affect the Earth's overall charge. The process of connecting something to the earth by means of a conductor is called grounding. So far, we have shown what happens when we carry a negative charge. But what happens when we carry a positive charge? Suppose you decide to wear a rubber raincoat over your cotton shirt. Again, the initial electrical charge on both garments would be neutral. Now, rubber has a stronger attraction for electrons than cotton. As a result, electrons transfer from the shirt onto the rubber raincoat. The raincoat now has a negative charge, and the cotton shirt a positive charge. If we remove the raincoat and wear only the positively charged shirt, look what happens when we touch the water tap. As usual, there's a spark. This time, electrons flow from the earth into the arm, and in so doing, neutralize or discharge the shirt. Grounding, the process where we connect a charged object to the earth, will discharge that object, whether it is positively charged or negatively charged. How do we know when an object is charged? The metal leaf electroscope can detect charge, even in very small amounts. It consists of a metal shaft, which has a knob on one end and very delicate metal leaves on the other. The shaft is insulated from the container which encloses it. When the knob is touched by a charged object, look what happens. We can explain this phenomenon by applying some of the theory we have just established. The initial charge on the electroscope is neutral. When the electroscope knob is touched by a negatively charged rod, a number of electrons jump onto the neutral knob. We call this process charging by contact. Remember that each electron repels every other electron, and the repulsive force they exert on each other will cause them to move as far apart as possible. Since the electroscope is metal, the electrons are not confined to the knob, but spread themselves uniformly throughout the entire electroscope. Because the electroscope now has a negative charge, the leaves will repel each other and diverge. If we touch the electroscope with a positively charged rod, the result will be the same. This time, some electrons transfer from the knob to the positively charged rod. The resulting shortage of electrons leaves the electroscope with an overall positive charge, and accordingly, the leaves will again repel each other. Charging by contact isn't the only way to charge an electroscope. Next program, we'll demonstrate a technique in which the charging rod never touches the electroscope. One way to acquire an electrostatic charge is to come in close contact with another object that consists of different material. Cotton, for example, has greater attraction for electrons than wool. Therefore, when these materials come in close contact with each other, electrons transfer from wool to cotton. The cotton now has an overall negative charge, and the wool an overall positive charge. Their opposite charges account for the static cling when you attempt to separate them. The easiest way to neutralize